Thank you. Okay. This is a project that I'm going to present today, which is in collaboration with the Standard Chartered Bank and QCware. And it's one of the several applications projects that have been sparked by the program at the USRA, which, thanks to the generosity of Google and NASA, is allowing anyone, well, everyone that successfully present a proposal and gets accepted to use the D-Wave machine, also the NASA Ames. So if you are interested, there is indeed the opportunity to write a proposal and get machine access. And this was the case for both Standard Chartered and QCware. And as it happens sometimes, USRA and NASA decides to collaborate with proposers. So this was one of these cases. And the case, the application use case that I would like to discuss today is from finance. And we have been exposed to some discussion on finance problems during the previous sessions. I'm not a finance expert, but my collaborator, Alexei, is around, so feel free to ask him more details about the meaning of all of this. But for us, for me and people like me, in the end, the problem is asset allocation problem, which is naturally fitting into a cubo form, where you have n choose m combinatorial problem, or you have to choose a certain number of assets out of a basket, and every asset has a certain desirability, which is encoded in the linear coefficients of the cubo, and a correlation with the others assets, which could be positive or negative, which is encoded in the quadratic terms of the cubo. And of course, these coefficients are derived out of financial data. And this is the case also for the test case that we're going to do. So they're essentially related to the Sharpe ratio, which is a measure of the expected return of an asset over time. Usually, there is also some hard constraints that you want to impose in your optimization problem in finance. For example, you have a limited amount of money, and you want to select only a certain number of assets, or maybe a weighted sum of those assets with the respective prices. Of course, usually we do encode these kind of problems, like with a penalty function, such as this one, which of course, generates a fully connected graphs with all sorts of precision issues, as I'm going to discuss. The cubo, as I mentioned, is obtained from real financial data, but instead of using the real values of the coefficients that would be derived through the portfolio optimization Markovitsian theory, you bucket the values into coarse-grained integers, where essentially you assign a linear coefficient from -15 to +15. We chose this bucketing. I'm going to say something about this. And you choose correlation values, which are integer values between 5 and -5, depending on what the covariance matrix is in your financial data. The cubo, the resulting cubo, has almost fully connected form. You can identify communities if you want, which are more connected nodes, but ultimately you really have a matrix which has some positive coefficients indicated in red, some negative indicated in blue, some almost zero coefficients, but in general it's very, very connected. And this is why we need also to embed this in a fully connected graph. The constraint, the hard constraint in our case, can be enforced by a classical loop of by running this problem for several shifted values of the linear coefficients, because the term for the cardinality constraints of the selected set is too difficult to embed given the precision issues of the machine. So what we do is we can adjust the rewards or penalties of the single individual assets so that the solution of the unconstrained problem has a certain number of assets. And you do this in a classical loop, like similarly as it's done for other problems that we discussed in the past, such as job shop scheduling. I'll say something about that. But for the test I'm going to show for a selection which goes from +15 to -15. The embedding is associated, as we know, with a quadratic overhead on the number of variables. And it's using the triad construction, which we are almost all of us familiar with. And as we know, beside a proliferation of number of variables, you also have precision problems associated to embedding. Indeed, the chains which are meant to encode the logical qubits after the embedding procedure, they need to be ferromagnetically coupled strongly. And this ferromagnetic bond is typically the most energetic term of your Hamiltonian. So it determines the rescaling of the remaining part of the Hamiltonian. And this is an issue especially for the local fields, because the local fields in the Ising embedded problem, no, they are determined by the linear coefficients of your QUBO plus terms that come from the QUBO to Ising transformation. They are rescaled by the overall ferromagnetic coupling due to embedding, and they are further divided by the length of the chain, which represents your logical qubit, because you have to assign this linear coefficient to a chain. And what we usually do, we split it over the whole number of nodes of the chain. We tried different ways to assign the local fields, but we didn't have good results. So we're still doing this procedure, and this procedure leads sometimes to values which are smaller than the nominal precision due to intrinsic control errors of the machine. So the problems I'm showing to you today are at the limit of the precision of the machine, and we're certainly hitting the, the moment where we could not go further without some other tricks. So these are the results based on a vanilla usage of the D-Wave machine, where vanilla means using the state-of-art technology of the previous papers of our group and other groups. So you run many times, millions of times. You use gauges. You average over at least 10 instances. You compute the time to solution, which is the median expected runtime to obtain the ground state with 99% probability. And you do this doing majority voting at the end of the embedding procedure. You set the parameters by scanning over different J ferromagnetic couplings. You find the best one for your instance set. And you run for several annealing times. And you find, for example, in this case, that the fastest runtime is the more optimal one. What you end up with is exponential scaling of complexity of your performance with respect to the number of assets of your problem. This is not surprising. This is actually quite consistent with the previous results starting from 2015 on fully connected graphs. To be fair, previous results focused on Sherrington-Kirkpatrick instances with bimodal distributions and no local fields. But in the end, even by looking at the repeated experiments which were presented by Peter in a couple of days ago, what we observe is that we fall with these new results substantially within the expectations of the performance that we obtained on the Sherrington-Kirkpatrick models a few years ago. So the machine seems to be performing rather consistently on fully connected graphs, irrespectively somehow of their coefficient structures, up to an order of magnitude of expectations. we are going to, for sanity checks and for reference point, we are going to confront this with the classical benchmark. In finance, a popular and efficient benchmark, especially for instances which are not very large, otherwise is not guaranteed the ground state, is genetic algorithms. So we tested this against genetic algorithms used by Standard Chartered finance research team. And what we observe is that for the median runtime, the genetic algorithm have a better scaling, at least for a small number of assets. And considering only the annealing time and nothing else, no overhead of any sort, we see that the quantum annealing scaling is substantially worse. However, there is a large, several order of magnitude speed up for a small number of instances. But at the application scale, actually not the application scale, but at the largest scale that we can test, we have a competitive runtime with the laptop. So that's somehow the result. However, to be fair, as I mentioned, for the largest number of variables, we do hit precision limits. Sometimes we never solve the problem. So we actually, at 54 variables, we solve 50% of the instances. At about 60 variables, we solve 30% of the instances. So we tried to say, okay, how do we solve the remaining instances? What can we do? So we started doing a pre-processing routine, which is very similar to the one that D-Wave does for repairing the chains after an embedding goes wrong. It's just substantially a greedy heuristic search that is guided by the local fields of your problem and the nearby contribution of every node. And by running this simple algorithm, we see that most of the small instances are solved very fast and immediately by this algorithm. But starting from 48, 42, 48, this greedy heuristic search falls short and solves only 50, 60, 70% of the instances, and falls about 5 to 10% away from the ground state in terms of bit flips of your solution strings. So we decided to take the solutions of the greedy heuristic search and to feed them to a reverse annealing procedure. So we use the reverse annealing feature of the new machine. So we initialize essentially the machine with the solution of the classical greedy heuristics, and then we ramp up the transverse field for a specific number of microseconds up to a specific region of the schedule, typically around 0.4, where the magnitude of the problem coefficient energy and the local fields, the transverse fields are more or less the same. Then we pause for twice the time that it took us to arrive there, and then we come back with the same speed as we ramped in the beginning. So that's actually an arbitrary protocol. It's not physically savvy, okay? But it is after trial and error, and is consistent with the intuition that we want to start from a local minima, arrive to a region where we can shake things around using quantum fluctuations, and then come back. So what are the results? Well, the results are that it works somehow. We scanned over 0.4 region of the schedule. You see that, those are the scans. And we run this for 1 microsecond speed, 7 microsecond speed, or 15 microsecond speed. So you always see that the performance, this is the time to solution, is around, in the best case scenario, is between 10 to the 3 or 10 to the 4, as opposed as the previous bottleneck solution where we hit 1 million runs required. So without considering the time of the pre-processing, which is very, very fast, to be honest, we can actually use the annealing only from these ansatz and obtain a better scaling and a better, well, scaling we don't know yet, but a better solution. certainly a constant speed up, which is more than an order of magnitude with respect to the vanilla kind of runs. To be fair, we could initialize also genetic algorithms with pre-processed results, and we did that, and indeed also the genetic algorithm performs better if initialized by the grid heuristic ansatz, and by about an order of magnitude. All of this is with very small instances and without any error correction code. So it's still very subject to all the precision issues that have been elucidated by also Helmut and Daniel in the previous talks. However, we're very excited about the next upcoming machine with the Pegasus architecture, which will allow us to push this test to n equal 180. Which will be certainly in a regime where the scaling will be more significant, and also to use error correction potentially so that we can run up to n equals 60, but with error correction, error suppression structures in the machine. So to conclude, we tested this to have a baseline on how the machine performs against some sample finance optimization problems which are relevant for the finance industry. This is actually part of a classical loop that you need to do in order to find the solution with a given budget constraint, because we cannot encode hard constraints without running in precision issues. There are a lot of questions about reverse annealing. These are the first investigations that I'm aware of reverse annealing in applications, in embedded problems. And what I'm more interested about is correlate the performance of reverse annealing with the number of bit flips required to reach the ground state from an ansatz solution, which I believe would correlate. And going further, we are going to use other features of the machine. The new machine, for example, extend the J range. That should improve the precision results. And also, as I mentioned, test this in the new architectures where scaling will be way more significant. Thank you very much for your attention, and you feel free to contact me or my collaborator for further discussions. Thanks.
So we have time for one question for Davide. So Catherine has a question.
So thanks for that. So they're kind of, every time you do a gauge transformation, it's also possible to maybe change your J value or change your reverse, how far back you go, to, all of the parameters available to you could be modified every time you set a new problem, basically. But I have the impression that you sort of pick a fixed J that you've decided is the best J, and do you set all these parameters, find the best one in advance, and then use them throughout, or do you vary them during the tests?
I do not vary them during the test. I do pre-characterize over an ensemble of instances which are not the ones that I show, and then I use the values that I derive to choose as fixed parameters for the runs, and then I check whether they were a good choice, just cheating in some sense, and see, okay, yes, they were a good choice. So this is how I do the runs so far. I agree that you could somehow, in parallel, analyze the performance of your runs, since they're all independent, and decide to adjust and do maybe half of your runs in one way and half in the other. As a matter of fact, I agree that for the parameter setting of the embedding, for example, it might be convenient, and we have some code doing this, to not set a specific parameter, but just run a bunch of parameters close by, so that you hit the performance when the resonance is, whatever the dynamics is, with more probability.
All right, let's thank